All right, so we're going to be looking at double linked lists. And so to start, we'll be doing a little bit of review on linked lists, but we won't be going too in depth. So this is just the last slide of the last one, where we can see that linked lists are a way to store data. And they can store ordered data, and they're similar to arrays, but linked lists tend to be more flexible. And so we've talked about how linked lists are just a collection of nodes that are stringed together, and they're stringed together using pointers. So their fields, the fields of this record, they would have a data, which contains a value, and the next, which contains a pointer to another linked list node item. And the end of a linked list is just the last node in the list, and then this node would have a null pointer, so it would have a pointer that points to nothing, and that's usually represented by like a little circle. And so we go over how to build a linked list, and generally what you're going to be doing is you're going to be creating the individual nodes of the linked list items, and then you're going to be connecting them all together. So you're going to be like tying these little pointers up and pointing everything in the right direction. And so, for example, this is the commands needed to build this list. So we would first be creating the linked list and setting its pointer to the first node in the linked list. And so that would be creating an item. So it would have the data of 8 and have a null pointer. And then you just set the pointer of L next. So you would set its pointer to the next item that you're going to be creating, and the next element in the list. And that would be item 2. And then same process again, set that pointer to null. And then grab its pointer. So you're going to be connecting that to a new item that you're making. So you're making another item that's going to have item 2 with a null pointer, and you're going to set this pointer to that item that you just made. So yeah, and then and that's pretty much how you want to build this linked list. Yeah, so in the case that you want to put 4 before 8, what you would do is you would create another item 4, and you would set its pointer to the head of the linked list. So you would set its pointer to the first item in the linked list, and that would set 4 to be in the beginning of the linked list. So yeah, it would be pretty much this one, since this one's creating an item with 4 and setting its next pointer equal to the head of the linked list. Yeah, so we just store the address of item in X, and then this is the whole process where we're creating an item and we're setting it equal to 4. And so this looks at the implementation of a linked list. We went over that last time, but it's pretty simple. Like, it's pretty much just you have a struct node, and it's going to contain some data. It's going to hold data, and it's also going to hold a pointer to the next. It's also going to hold a pointer, and this pointer is going to point to another struct of a node. So it's going to you pretty much have a pointer to another node. So that's a linked list node, but as far as the linked list is also simple. It's just going to have a head pointer, and then when you first create the linked list, it's going to set that head to null, because initially you're going to have an empty linked list. So yeah, the constructor initializes the head pointer to null, and this is an empty list. And then appending is it's gonna be yeah, so this is how you add a node at the end of the list. So let's go back to our code and kind of refresh our memory. So yeah, we actually don't have we don't have a linked list proper here, but pretty much how this function would be working is, that's not it, is it would take in a value and then it would traverse through the linked list. Okay, so first off, it takes the value in. So let's say you call it with 5, it's going to create a new node, and it's first going to call the function to create a new node. It's going to set its data equal to the value. So it's going to make a node, it's going to have value, and it's going to set its pointer to the null pointer because you're adding at the end of the list. And then this part is just you traversing through the list and finding the end of the list. So if it's empty, you're just going to set the head of the linked list equal to this pointer that you just made. Otherwise, you're going to create an iterator which will loop through the linked list. So here we're creating a node we're going to create a pointer that's going to be looping through our linked list, and you're going to set it equal to head, and you're just going to keep taking the next you're going to keep following its pointer till you hit the end. So you check that its next pointer is not equal to a null pointer, and you just take the next one. So then you set the iterator equal to its next node. Once you hit the end, when this breaks, is when you're at the end, and so then it's just a matter of setting, instead of the null point, the current dot next equal to null pointer, aka the end of the linked list, we're just going to set it equal to the new node that we just created. So if we whiteboard this out, it would look a little bit like, let's see if we have, let's go back to the other one. It would look, I can just whiteboard it out. So let's say you have a how it would do this is, let's say each linked list node has data and also a pointer, and so I'll represent that with arrows. So let's actually make these different so that way we know these are different nodes. If we have a head and it's pointing to the beginning of our linked list, how this is going to work is we're going to make a current. This is how the iterators work, is that you make your own pointer, and you just set it equal to, in this case, head. So we copy over here. We set it equal to head, and if heads doesn't point to anything, then we just add the new node that we made. So let's move this let's make this a new node. Let's say we call it our append function. Append e linked list dot append e. What we do is we just make a node e, and we set its pointer equal to null, so it'd be a null pointer. And once we got that, the next part is we loop through the list. So we're going to be setting current equal to a, and if a has next, which I'll set the arrows up right now just so it's not confusing. And I'll go through it again. But while A points to something, we're just gonna set current equal to that pointer. So while while this has a pointer, while the node that we're pointing to has a pointer to another node that's not null, we're just gonna keep moving current's pointer to that next node. So initially it'll be A, but we see that A points to B, so we'll change current to B, and we see that B points to C, so we're gonna move current again to C, and we also see that C points to D, and we're gonna move it again. And when we hit D, we see that D doesn't point to anything. D doesn't point to any new node. So what we do now is we grab D, we grab its pointer, and instead of having it point to nothing, point to null, we point it to this new node that we just made. So this new node that we just made is going to be the end of our linked list, and that's going to be how append is going to work. And you can see in here, this is the code for it. So it's going to find the head. In this case, it'd be inside of a class, so it's just going to call this head. And it's going to loop through, find the end, and assign this new node that we created to the end. And so this would be the display function. It's very similar to the function we had over here, where yeah, so we're going to print out the node, we're going to print out the data, and we're going to keep it moving. So yeah, so it's going to find the head, and while head's not null, it's going to print its data, and then it's going to set the iterator to the next one, and then it's going to print it out. It's going to just print everything that it made, pretty much. Yeah, so it starts from the head, traverses through the list while printing each node's data. It uses a while loop and advances the current pointer to the next node in each iteration. This is a destructor, and the destructor is responsible for freeing memory used by the linked list when the object is destroyed. It iterates through the list using while loop, and it deletes each node pointed to by the head and advances head to the next node until the list is empty. This is just so when you know that you destroy your linked list, you're not taking up any extra space. This shouldn't be too important though, at least not here. And so if you were to make a linked list class, if you want to first initialize it, this is how you would do it. You would just call the linked list, and you create a linked list object, and in this case it'd be called mylist. And then you populating that list would just be you grabbing that list object and calling append 10, append 20, append 30, and then this would create you a linked list with 10, 20, and 30. And then you're just displaying the contents. So basically, you got a node which represents data, and the data, and it also has a pointer which points to the next node in the linked list. The linked list class encapsulates the linked list operations, so it'll have a header which will point to the first node, and it'll have an append function, and the append function is just what we went through earlier, where we're just creating new nodes and adding them to the end of our list. And then we also have a print function which will print the elements of the linked list. And I'll have a destructor. So there are three types of linked lists. There's single linked lists, where you just have a list that goes from beginning to end, and it looks kind of like this, where we have nodes with reference to the next node in the sequence, and then traversing through this linked list, it's straightforward. You just keep taking the next one. There's also double linked lists, where each node has a previous and a next pointer. And there's also a circular linked list, which is like a single linked list, but instead of this, the last node pointing to null, it instead points to the head, so the beginning of the linked list. So it will loop around in a circle. And so yeah, this is just a slide describing the double linked list, which is same as I mentioned before, where we have nodes with next pointers and previous pointers. So you can move from node from next pointer to previous pointer in this list. Circular linked list. The last node. Yeah, this is the circular linked list where the last node of the list points to the head of the first node in the list. And this basically goes through the time complexities of operating on a linked list. Insertion means you're just making a new node and you're adding it to the list. You can pretty much insert nodes anywhere you want in the list, since each node is a little bit independent of the last, and these are just objects, and the only reason why it's a list proper is because you're maintaining the pointers between these nodes. Like, you're making sure that this one properly points to this one properly points to this one properly points to this one. Because otherwise, these are just independent nodes that exist without any knowledge of the others. Deletion would just be removing a single node and then adjusting the pointers as you need be. And this can be done anywhere in the list. But searching requires iterating through the entire linked list until you found it or until you reach the end. There's no way for you to there's no way for you to know whether this list contains a letter Z or not without traversing through the entire list. Like, you can't just look at this and be like, all right, well, it's alphabetically sorted, so if we have a Z, it's going to be at the end. Like, there's no way for us to just like jump to the end and see like, oh, is the last element Z or is it E? The only way we can do that is by looping through the entire array in our iterating functions. So that would be making a current pointer and pointing it to the node and just checking every single node if there's the element you're looking for. So the advantages of linked lists are that it's dynamic, so it can grow and shrink dynamically as memory allocation is done at runtime. And insertion and deletion, adding or removing elements is efficient because you're only doing you're only changing one little node. And then it's also really flexible because you can just you don't need a contiguous block of memory. You can pretty much your computer will take care of finding memory to insert the data you need for this linked list, and it will keep track of linked lists. But one of the disadvantages is that you can't just randomly access like any value of the linked list. You can't just directly access any value. You would have to traverse through the entire array to find the linked list. You would also need to store memory for the pointers. So if a pointer, you have each node has pointers, so these pointers aren't necessarily free, they take up space. And in the arrays, you don't necessarily have that because all the elements of the array are going to be in contiguous space. So it would just, in a normal array, the data would just be by itself and you wouldn't need to have a pointer to the next node. So yeah, that's one of the disadvantages. This is a single linked list. This is an implementation. It's very simple. You've got the node, it's got its data, and this is a linked list which wraps around a node. And in the beginning, when you first initialize it, its head is empty, but when you add it, when you add data to it, first you're going to be creating a new node, and then you're going to be setting the head to this new node. So so this line creates a new node with the data. You set this node's next pointer equal to the head of the linked list, and you set the head of this linked list to this new node. this is a doubly linked list. And so as you can see here, we hold two pointers. One pointer is going to be pointing to the next node, and one pointer is going to be pointing to the previous node. And so this allows you to traverse through the array backwards and forwards. And so for this purpose, you need the extra node. Adding a node to this list is similar to the previous version, where you're creating a new node, you're setting that new node's next pointer equal to head, and if the head isn't empty, if the linked list isn't empty, you're also going to be setting the previous value of the header equal to this new node that you created. Otherwise, you won't have to worry about it, and then you're setting the head to this new node. So I'm gonna whiteboard this because that's kind of how it is. So let's say you have a list that looks like this. So this is how the double linked list nodes look like. So they're gonna have a previous pointer, they're gonna have data, and they're also gonna have a next pointer. So we can imagine the head. This would be like the double linked list class that kind of wraps around these nodes. But when let's say you have a list that looks like this, where you have A, B, C, and D, and you want to add E to the beginning of the linked list, what you would be doing is you would first, okay, so let's look closer at this linked list. So before we talk about adding to it, so A has a pointer that points to B, and B also has a previous pointer that points back to A. And you see every single node that is connected, they are going to have a next pointer which points to the next node, and a previous pointer that connects to the previous node. So that we have a two-way street on every single node connection. And so adding a new node to the beginning of this list would look first like if we call add E on double linked list. So let's say we have double linked list dot add E. What we would first be doing is we would be creating this E node. We would be setting previous to nothing, because this is going to be the new beginning of our linked list, and we would be grabbing the next and pointing it to the beginning of the linked list if it exists. And then we would also be grabbing the head of the double linked list, and we would grabbing this previous arrow, and we would be pointing it towards this node that we just created. So we create this new node, we move its arrows to properly fit in our function, and then we also update the head so that we have E as the beginning of our class, of our double linked list. And so that's reflected here. In a circular linked list, all that means is that the last node in the linked list points to the beginning of the linked list. So I'll whiteboard this out. So let's go back to the whiteboard. And let's go over here because this is our linked list. This is our single linked list. And so what that would look like is if this was a circular linked list and we want to properly show that, D, if our initial linked list, let's just consider these lists and these nodes initially. Since D is our last node, and we know it points to nothing, what we would do is instead of having it point to nothing, we just point it to the beginning of our linked list. And so we keep on hand what the beginning of our linked list is with the head node, but for purpose sake, just to make it look like it's a circular linked list, we're going to point it to A. But just know it knows where A is because we have a head node, which knows where A is. So we keep track of the beginning of the linked list, and we keep track of the end of the linked list. And so we just point it to the beginning. And adding a new linked list would just be the matter of knowing where the last node in our linked list is. So we know that D points back to A. So we just grab it, and instead we point it to our new node. So again, if we're appending E to the end of our linked list, we would just be grabbing E. I don't want it to curve. I don't want this one to curve. Pointing it to E, and then we would be grabbing E and pointing it to A. So that keeps the circular aspect of our linked list intact. And then we still have we would then still have a circular linked list. And that's reflected in this code. So first we make the new node with the data. If head's empty, if the list is empty, we just set the head equals to this new node, and we just set the new node equal to its head. So it's a single node circular linked list, which just loops around on itself. Otherwise, we would create an iterator, which will loop through the entirety of the linked list until it reaches a node where its next pointer isn't the beginning of the linked list. And so I'll whiteboard this out just to break it down, but it creates a current node, and this is going to be our iterator. This is how we're going to loop through the linked list. And it will just take its next until its next pointer isn't the head. And it's going to grab the pointer from the current to the next, and instead of pointing it to the head, we're going to grab it and we're going to point it to the new node. And the new node dot next is going to be equal to the head. So that's kind of like it's kind of what I just showed you, where we set our new node that we just created equal to the beginning of the node. But I'm going to do it one more time just to make sure we understand. So first, we're going to set current equal to the head, the beginning of the linked list. And while current, which is going to be our iterator, while current's next, if we were to take current.next, it would give us B. But while current.next is not equal to the head of the linked list, the beginning of the linked list, we're going to keep moving. So current's next is equal to B, and B is not A. So we're going to move our pointer. So we're going to take its next, we're going to set current equal to its next pointer. We're going to set current equal to the node at its next pointer. So current has a pointer which points to next, and we're going to move current equal to that. So we go to B, and we see that B.next, so in this case it would be C, is not equal to A. So then we move the current pointer again. We see that C's next pointer is D. That's not equal to A, so we moved again. And initially, D did point to A. So D would have pointed to A. And when this happens, that is when we did our magic, where we're grabbing this pointer, we're moving it, we're pointing it to this new node we just made, and that doesn't have any nodes pointing to it. And then we grab our new node, and now we're going to set it equal to head, the beginning of our pointer. And that creates our circularly linked list. So they can be very effective. Linked lists are very effective in insertion and deletion. They can take less time complexity compared to array data structures. You also sometimes use it for stacks and queues and other abstract data structures. Some applications of linked lists include creating stacks and queues. You can use it for representation of trees and graphs, which is another topic that is another type of data structure that you'll look at later on in the course. You can also use it for dynamic memory allocation. That's something I talked about in the last video. Um, it is used to represent sparse matrices, polynomials, bunch of this other stuff. I won't hop on this slide for too long. A node, so back on the topic of doubly linked lists, you can insert a new node in, you can insert a new node into the doubly linked list in multiple different types of ways. So you can insert it in the front of the doubly linked list, you can insert it at the end of the linked list, and you can insert it between two nodes, whether that's after a given node or before a given node. And so to add it to the front, add a node to the front of the double linked list, this would be, I'll whiteboard it afterwards, but let's just break down the steps. So first you create a new node, so you allocate a new node, you put the required data in the new node. So if you're making a new node that with letter C, or no, with the letter F, you would put F inside the data of the new node, and you would make the next of this new node, you would make the next pointer point to the head of the double linked list, so the beginning of the double linked list, and then you would grab the current head, the beginning of the current double linked list, and you would point the previous, you would grab its previous pointer and you would point it to the new node. And then lastly, you would change the beginning of the double linked list to this new node. So let's whiteboard this up. So that's kind of like what we did over here, where we are, that's actually what I just showed you. But let's do it again. So let's just go ahead and delete these. So let's say we know that the head of our doubly linked list is A, B, C, D. And head points to A. And we want to add E. So we first create a new double linked list node. So we create a new node. And we set its next equal to the beginning of A. So we first populate with the data we want. So in this case, E. We set its next equal to head. In this case, it's A. So we set it to equal to A. We then set A's previous pointer, which at this current point points to nothing. We set that equal to this node we just created. And then we set head, we move it to E, since E is going to be the new beginning of our linked list. Yeah, let's look at, so that's this process where we're changing the head to this new node we made. We're setting the pointers to the proper location. So E's next pointer is going to be A, and A's previous pointer is going to be E. And previous is also still going to point to null. I'm going to take a little break right here. And so this is what's the code of this previous operation that we just mentioned, where we're pushing nodes into our double linked list in the beginning of the double linked list. So you can see the steps broken down. So first we allocate the new node, we create this new node, we fill it with the proper data. So we set new node data equal to new data. Then we make the next of the new node as a head and the previous as a null. So we set its next pointer. So it has a next, is a pointer, next pointer, and that's going to point to the next node. And we're going to set this equal to the head ref. And we're going to set its previous pointer to equal to null. And as long as there is a beginning of the double linked list, we're going to grab its previous we're going to grab its previous pointer and set it equal to this new node we just made. And then you're going to change the head to point to this new node. Yeah. So yeah, same case. This is an explanation of what I just mentioned, so I'm not going to repeat myself. Update the previous to the old head, update the head reference, this is adding a node in between two nodes. So adding a node after a given node in a double linked list. We're giving a pointer to a node as previous node. As a new node is inserted after the given node, this can be done using the following 6 steps. First, you want to create this new node. So say new node. Insert the data into the new node. Point the next of the new node to the next of the previous node. And you're going to want to point the next of the previous node to the new node. And you're going to point the previous of the new node to the previous node and change the pointer of the new node's previous pointer to a new node. I'll whiteboard. I think there's a better explanation in these coming slides. So I'll whiteboard this process out as well. So if this is what our linked list looks like, and we want to insert E after B, let's say that this part is how it looks like. That would just be the process of changing these pointers. So first, if we're going to put add insert after, and we're calling it with E and B. So let's say we call this function, and we put this E node after B, and we know where B is. So let's just say, for simplicity's sake, we know where B is. So that would just be the process of grabbing B's next pointer. Okay, so first, obviously, we make E. So we make this node, and we know that we're going to put it in between B and C. So when we make this node, we're going to grab its previous pointer, and we're going to point it to B. We're going to grab its next pointer, and we're going to point it to B's current next. So B currently points to C, so we're going to point E to C. So we're going to set that equal to B's next pointer. So since E points to C, we're going to point it to C. And then we're going to grab these two nodes, and instead of having B point to C, which we just made E a copy of, we're going to instead point it back to E. And then C, since C previously pointed to B, and we want to insert E in between B and C, we're just going to grab its previous pointer, and we're going to point it to E. And that's inserting this node in between two nodes. And so that's this process where we're grabbing these two old links and we're breaking them apart, and we're kind of putting this in between these two. This is the code for that. So same thing, we're creating this new node, we're filling it in with the proper data, we're making the next of this new node as the next of the previous node, we're going to make the next of the previous node as a new node. So that's changing these pointers around. So previous node, new node, new node. Okay, so let's break down these two lines first, since this is our new node. So we're going to grab the new node's next, and we're going to point that equal to the previous node's next. So that's where we're grabbing E's next pointer and making it equal to B's old last pointer, last new next pointer. And then we're going to make the previous node as the previous node. So if we're going to be putting E after B, we're just going to set that equal to the previous node. And then we're also going to make the next of the previous node as equal to our current node that we just made. And also, if the new node, if the previous node pointed to something that actually existed and wasn't just a null pointer, we're going to set that one's previous pointer equal to the new node. And that's the case of C. So we're going to update C's previous pointer. And that's the code for it. Insert after function is used to insert new node with a given data value after a specific node in double linked list. This is going to be the same one, I believe. Wait, is this the same? Insert after. Oh, okay, yeah, no, this is just explanation. So yeah, previous node is null. This is just going to be explaining the same things I just said. So I'm just going to skip through this because I just explained it. Update the previous pointer of the new node. Add a node at the end of the doubly linked list. This is just going to be the process of creating this new node, putting the proper value in it, setting its new next pointer equal to null since it's going to be the end of the linked list. If it's empty, you just make this new node that we just made, the head. Otherwise, we're going to travel to the end of the linked list, and we're going to make its next pointer equal to the new node, and we're going to change the previous pointer of the new node to the last node of the list. And this one shows it pretty nicely. We're just going to create this new node. We're going to make it D. We're going to make sure its next pointer points to nothing. And we're going to make an iterator, which starts at the head, and we're just going to loop through the entirety of the list until we hit the end. And we're going to grab the end node, and we're going to set it, instead of next, we're going to set it to equal to this new node we just made. And we're going to set this new node we just made, we're going to set its previous pointer equal to the end of the linked list, of the old linked list. This is the code for doing so. Pretty similar to what we've been doing. We make the new node, we set the data to be proper. Oh, this is actually the iterator, I believe. Yeah, this is the iterator. We put in the data, so we fill it with the proper data. This next node is going to be the last node, so we make sure the next pointer is going to be null. If it's empty, we just make this new node we just made as the head. Otherwise, we're going to traverse the end of the list until we hit the end. And then we're going to change the next pointer of the last node equal to this new node we just made, and we're going to make the last node as the previous of the new node. Yeah, so same case. This is going to be explaining the same thing I just went through. So I'm gonna skip it because I think I've been doing a good job with the whiteboarding. Please tell me I'm recording. Okay, I am recording, thank God. Traverse to find the last node. Yeah, connect the new node to the end. This is the circular linked list. There's no null at the end. Yeah. Two types of circular linked lists. They're both pretty similar. One just is one way. So all the nodes just have a next pointer. There's another type that is two-way. So it uses the two-way nodes where each node has a previous pointer and a next pointer. Yeah, so the only difference is that this is a one-way linked list. This one is a two-way linked list. So you can go backwards, forwards, backwards. And if you go all the way to the end, it loops back to the beginning. And if you go all the way behind, it also loops back to the beginning. So 2 loops. So the circular linked list, it's gonna have instead of a head pointer, it's gonna have a last pointer, and this is just so that we keep track of where the end of the linked list is properly. So yeah, this breaks down why we do that. Is for the insertion of a new node at the beginning, we need to traverse a whole list. Also for insertion at the end, the whole list has to be traversed. Instead of starter pointer, we take a pointer to the last node. Then in both cases, there won't be a need to traverse a whole list. So insertion at the beginning or the end takes constant time, irrespective of the linked list. And you can insert into a circular linked list in 3 ways. You can insert in an empty list, insertion at the beginning of the list, insertion at the end of the list, and an insertion between 2 nodes. Because this is very similar to just double linked lists, you just have instead of, that's not what I want to show. Instead of having a head, you just have an end. So instead of head, this would point to the end. That's the main difference. When the list is empty, the last pointer will be null. Yeah, so after insertion, T is the last node, so the last pointer points to node T, and node T is the first and last node. Adding to an empty list is constant. It's similar to what we've been doing. In case of an empty list, it's what the? Oh, okay. Oh, so this is only for empty lists. So yeah, we're going to create a new node, assign the data, and then you just signed its next equals to last is equal to temp, and you return this. Yes, you make a circular node, and you return last. So yeah, we're going to create a node, say T, make T.next equal to last.next. So we have a pointer pointing to the last node, and its next pointer is going to be 6. So this node we just made, we're going to make its next pointer equal to this thing we just made, equal to 6. So last, and then we're going to set last dot next equal to T. So we're going to take this pointer and move it to T. So T is going to point to 6, and 8 is going to point to 10. Oh wait, is this a circular linked list? A circular linked list. Okay, so this is a circular linked list, but not a doubly circular linked list. Oh, this whole thing has been with circular linked lists, not double circular. Okay, that is very confusing. Okay. Okay, so yeah. Insertion of the being list. Insertion of the being list. Where were we? Yeah. Okay. Yeah, so this is it after insertion. So 8 is going to point to 10, and 10 is going to point to 6. And we also need to update last to be 10. So this is the code. Add beginning. If last is null pointer, we're just gonna do this special operation where we're adding to an empty list, and that's gonna be easier. Otherwise, we're gonna create a new node. So this new node is gonna be the node we're gonna add. We're gonna assign it with data. So its data is gonna be the data we're adding, and we're gonna be adjusting the pointers. So its next pointer is gonna be equal to the last pointer's next pointer. So in this case, it was 8 and pointing to 6. This 10 is going to be pointing to 6 instead. And the last, the old last node is now going to point to this new node we just made. Yeah. And that's for inserting at the beginning of the list. The ending and the beginning doesn't really matter. I mean, a little bit, but the thing is, it's just because it's like circular. Insertion at the end of the list, this is going to be similar to the beginning of the list, but I assume in the previous case we're not updating last, but in this case we are going to be updating last. Yeah, so T's next pointer is going to be equal to last. The last is the next pointer, so 10 is going to be pointing to 6. 8 is going to be pointing to t. That's this. Last.next is equal to t, this new node we just made. And last, we're going to update this pointer. So this is going to be the same as inserting at the beginning, but instead of, we're actually going to be updating last. So yeah, that's the only difference, is that we're updating it. Instead of pointing it to 8, we're pointing it to 10. This is the code for adding to the end, and it's the same thing as the other code, just we update last. So literally the same thing, same lines, temp.data, yeah, same lines. The only difference is we update last. So last equals to 10. So instead of last pointing to 8, it's going to point to 10. Same code. Insertion between two nodes. We just need to find the node that after which t needs to be inserted. So let's say we're looking for p. You're gonna update the pointers, and so hopefully by this point you're able to figure out that linked list, we're just moving pointers around. So if you can kind of like imagine moving pointers around, it can get really easy. So like this is Excalidraw, and it has a bunch of nodes with you can make linked list nodes. You can move these pointers around as long as you imagine that as long as you can get to a point where you're like moving these pointers around, you can kind of wrap your head around it a lot easier, because that's the main thing. So yes, you search for the node after which t needs to be inserted. So that node's p. You make t.next equal to p dot next. So and then you set p dot next equal to t. So let's say we're gonna add 12 in between 8 and 10. What you're going to be doing is you're going to be moving the pointer, instead of 8 pointing to 10, you point 8 to 12, and then this new node, it's going to point to the previous pointer that you just removed. So we're going to set 8 pointing to 12, and then 12 pointing to 10. And because you have to traverse through the entire array to find the node that you're going to be inserting, it has a time complexity of O and N. Because the worst case scenario, you have to loop through the entirety of the array to find the node you're going to be replacing. Node after. So this is the code. If you have an empty list, you're going to return an empty list because you're not going to find the node you're looking for. You're going to create two nodes, a search node and a temp node. The temp node is going to be filled with the new data they're going to be adding, and the p node is going to be the search node. It's going to loop through the entirety of the list to find the node that you're looking for. So this is just it searching through the array, and it's just going to be looking until it finds the node it's looking for. So it's going to keep looping through until it finds the last node. So it checks if p is equal to last, which last is the node you're looking for. You find it and you replace it. Okay. Checking for the last node. So if it's the last node, okay, so it's going to loop through the entirety of the array, and if it finds it, it's going to set this last equal to this new node that you just made, and it's going to return the last node. Okay, so no. This whole thing is actually in the case that it finds it. So if P is, uh, if you find what you're looking for, you create a new node, you sign the data, so temp data is equal to data. You change the links, so temp next is going to be equal to P next. So you found the node you're going to be replacing. You change P next equal to this new node we just made. So this would be the case of 8 pointing to 12. If this is the case that it's the last node, you want to update the last node. So you want to update the pointer if the node you searched for is the last node. And if you loop through the entirety of the list and you can't find it, you just say that you couldn't find it and you return early. Some operations on circular linked lists are similar to the single linked list. Insertion, deletion. Deletion in a circular linked list is just if you delete the last node, you just gotta locate the node before the last node. And you keep the address of the node next to the last node in temporary, and you delete the last node, and you put temp at the end. So you would just be moving the last node equal to the node just previous that, and then you can delete the last node. So yeah, a linked list is an abstract data type that holds a collection of nodes. Linked lists are a form of sequential collection. Accessing elements in a single linked list must be done sequentially from beginning to the last. And that kind of ends this part. So that handles pretty much everything, all of linked lists. We looked at double linked lists, we looked at circular linked lists, and I made this code to break down double linked lists, but I think the slides kind of handled it. But let's just run this code just because so we won't waste it, I guess. To compile, we're going to be calling, I have to change into the directory we're going to be working at. So this is double linked list. We're going to compile it first. So G++ double linked list.cpp. We're going to create an output executable, and we're going to call it double. We're just going to call it the same thing, double linked list. And then we're just going to run that as an executable, so double linked list. And this shows us some code this shows us the example of 10, 20, 30. So let's just loop through this. So we create our double linked list, we push 10, we push 10 and we print. We push 20, we push 20 and we print. So that's this line. We push 30, we push 30 and we print. We append 40. So we put 40 at the end of the linked list. Pushing is going to be the act of inserting it to the beginning of the linked list, and appending is going to be inserting at the end of the linked list. So forward traversal through the linked list, if we're starting at 30, we go to 20, 10, and 40. Backwards, we're going to be starting at the end and looping backwards. So 40, 10, 20, 30. Inserting 25 after 20, we call DLL insert 25 and 20. And we can see it inserts 25 after 20. Deleting 20, it pops 20 out, so it would be the same as this without 20, so 30, 25, 10, 40, and we can see it works properly. The code is going to be similar to what we looked at in the slides. Yeah, I believe that's all. Thanks.